This lesson deals with an MC1530 Motorola op-amp. You can find these notes in the ECE302 ebook in Chapter 6, starting on page 17. What's shown below here is a schematic of an op-amp made by Motorola. And let me turn this sideways so you can see it a little better. You may notice here that this section to the left is what we had in our last video. It's a two-stage differential amplifier with current source biasing. Now what we're adding is some more circuitry to turn this into an op-amp. You can find a detailed explanation of the design of this op-amp in the Motorola application note AN204. Let's assume that all the transistors in the op-amp are identical, except for transistors 12 and 13. In the Motorola application note, they said that there were 3 transistors in parallel for transistors 12 and 13. These are the transistors on the far right-hand side of the op-amp, and they have the current that's going to go out of and into the op-amp when you put a load on it. Let's call this transistor like before, with a collector current, a base current, and an emitter current. And then let's show the 3 transistors inside, and we'll number those 1, 2, and 3. Let's assume that we're in the active region. The current coming in here is I sub C, and what's leaving is I sub C1, I sub C2, and I sub C3. So we're going to sum those 3. If we're in the active region, then this current here is going to be beta F times IB1, and then beta F times IB2, and beta F times IB3. Pull out the common beta F. What we've got is the sum of the 3 base currents. Of course, that's going to be equal to the current that's coming into the base of the composite transistor. The collector current for this transistor is equal to beta F times the base current. But if we're in the active region, the collector current for each transistor is going to be roughly I sub S times e to the voltage across the base emitter over 8F E sub t. But the voltage across the base emitter is the same for the 3 transistors. What we've got here is 3 times the value of the current that's in each transistor. For the same base emitter voltage, we'll have 3 times the current that flows in here. What this will allow us to do is to take the current that's coming in here and distribute it between 3 transistors, and thereby distribute some of the heat associated with each of the transistors as it's pulling a current through it with a voltage across it. You can think of this technique as increasing the effective area of the BJT by a factor of 3. In reality, that's how they make it. They make it 3 times bigger. And the value of I sub S actually scales with the area of the transistor. On page 17, diodes 3 and 4 are actually formed by putting a short circuit between the base and the collector of a BJT. We also call these diode-connected BJTs. And they form a current mirror when you connect it in the following way with the transistor. Here's this diode-connected BJT feeding into another transistor. Since the base emitter voltage of Q of D is across the collector emitter of Q of D, and this is about 0.7 volts, then that puts Q of D in the active region. The current coming here I'll call I, and that's equal to the base current of Q sub D plus the collector current of Q sub D plus the base current of Q sub I. But if we assume that all base currents are small compared to collector currents, then we could ignore this base current and this base current, and the current I would be the same as the current that's in the collector of transistor D. We also have the base emitter voltage of D the same as the base emitter voltage of transistor I because they're hardwired in parallel. That means that their collector currents are going to be identical. The collector current of transistor I is the same as the collector current of transistor D, but we just showed that that was equal to the current I as an approximation. The current in the collector of transistor I is the mirror image of the current that's coming into this combination of transistors. We can now do our 4-step algorithm for analyzing an amplifier circuit. We're going to assume that all the transistors are active, and then we're going to find the DC operating point. Now, because of all of the interconnections of these transistors, it's going to be very hard to solve for the equations if we have to solve for the base current. So let's assume that the beta F is extremely large. If I have a collector current in the active region, the base current is the collector current divided by beta F, and if beta F is approaching infinity, well then that base current's approaching 0. Now in reality, of course, we don't have infinite betas, we've got finite, but our base currents are small. They're usually in microamps or nanoamps. What I've shown here is a circuit we analyzed in our last video, which is the 2-stage differential amplifier with a current source biasing. This is a dotted box. What was coming out of Vout was 4.519 volts. And the current that was flowing in the transistor here was around 493 microamps. We assumed that hooking up something to it had no effect to get these numbers, so let's see if that's the case. Well, here I've got the base of a transistor. We're assuming that these currents are small compared to other currents. just going to label this as approximately 0, approximately 0, approximately 0, approximately 0, and approximately 0. Then we're assuming that the drop across the base emitters are about 0.7, so 0.7, 0.7, 0.7, 0.7. And of course, this is the voltage across these diodes 3 and 4. If beta is large, then the collector current is roughly the same as the emitter current, so that's the same as this one. Likewise here for transistor 11. And we'll talk about these other transistors shortly. I'm going to call this current I sub Z, this current I sub Y. And let's start to solve for things in here. If you notice, this is one of these diode-connected current mirror. So I'm going to solve for I sub Y by taking the difference of the two node voltages here. Let me scroll this up a little bit more. This node voltage is 0, and this node voltage is 0.7, and then minus 6 back to ground. 0 minus the quantity, 0.7 minus 6 is the voltage across this resistor, and we're going to divide that by 3.4K. That's on the bottom of the page here as 1.559 milliamps. The current that's flowing in here is going to be the same as the current that's flowing in here and the same as the current that's flowing in here. I sub C10 is the same as I sub Y because this is a diode-connected current mirror. The value of that current is also 1.559 milliamps. Go after the collector current of transistor 8, and that's going to be the voltage across this resistor divided by 6K. This node voltage here is minus 0.7 plus the 4.519 we found in our last video. And then minus this node voltage here, which is going to be 0.7 plus 0.7 and then minus 6. The quantity 0.7, 0.7 minus 6 subtracted from this node voltage here. And that's just right below. And then dividing that by 6K, we get 1.4 milliamps. We got that current, transistor 8. Transistor 10, and we know transistor 8, we can now solve for I sub Z. I sub Z is equal to I sub C10 plus the current in this direction, which is a minus IC8 plus 0. 1.559 milliamps, and subtract from that 1.4 milliamps for I sub C8, we get 159 microamps. That's the current that's flowing in this resistor here, and the drop across it would then be 159 microamps times 30K. That would be 4.77 volts. It's on the bottom of the page here. Difference of those two currents and then multiplying that by 30K. Let's find the current in the collector of C11 because the current in here is small enough to neglect. The current in this resistor is the same as the current here. The voltage across here divided by the resistance would be the current. This node voltage here is 6 and then minus the quantity 0.7, 4.77, 0.7, 0.7, then minus 6. And that's over here. That gives me 5.13 divided by 5K is 1.026 milliamps. Voltage across this resistor is 5.13. Let's solve for the collector current of transistor 13. What I have here again is one of those diode-connected current mirrors that we talked about on the previous page. The current that's in here is roughly the same as the current here. We assume beta F is large. And then the current that's here would be the mirror image of this one. But remember, there's 3 transistors in parallel, so we're going to have triple the value. The current that's for transistor 13's collector is going to be 3 times the value of transistor 11. That's 3.08 milliamps. Now we can go get transistor 12. Transistor 12's current's coming in here, coming back out. That's going to be equal to I sub Z plus I sub C13. I sub C13 was 3.08 milliamps. And I sub Z was 159 microamps. So adding those two together is about the same number, but to be more precise, it turns out to be 3.239 milliamps. And lastly, we could solve for V out. The voltage V out here, you just go back around the loop this way, back to ground. V out is equal to minus 0.7, minus 5.13, plus 6. And that's 170 millivolts. In other words, 0.17 volts. Again, we're assuming the drop is 0.7 and the value of beta is infinite, exactly the right values, but what's happening here is they're trying to shift the level of our power supply through these transistors to be roughly sitting at 0 volts. We normally do this with a blocking capacitor in our previous amplifiers, but putting a capacitor inside an integrated circuit takes up a lot of space. In fact, about the biggest one you could put in would be about 10 picofarads. That would take up about half the size of an op amp. We call this level shifting, where we're using the drops across PN junctions and resistors to drop the level of the voltage from the power supply to roughly an output voltage very close to 0. Now that we solved for the collector currents, we should check that the assumption that the base currents were negligibly small is a valid one. So we found the collector currents assuming that beta was a super big number, but now let's put in a reasonable number for beta F and see what the base currents are and see whether they were negligible or not. So dividing the collector current of 8 by 50, we get 28 microamps. The collector current of 10 by 50, we get 31.18 microamps. The collector current of 11 by 50, we get 20.52 microamps. Collector current of 12 divided by 50, we get 64.78 microamps. And the collector current of 13 dividing by 50, we get 61.6 microamps. Let's go back to the previous page and see where those currents are and see whether they were negligible or not. Here's I sub B8. We solved for this to be with a beta F of 50 to be 28 microamps, and that's the current that's leaving this node, and there was a collector current here of 493 microamps. That's about 17 times bigger than this, so that was a pretty good assumption. For transistor 10, we had a current going in here of I sub Y, which was 1.559 milliamps, and we assumed that current all went into here, and nothing went into here, but the value of the current here is 31.18 microamps. 1.559 milliamps is 50 times greater than the base current of Q10, which was 31.18 microamps. So that was a pretty good assumption. For transistor 11, we solved for the current here and found that it was 20.52 microamps. The current entering is I sub Z, which was equal to 159 microamps, so pretty small. And of course the current coming in here was I sub C8, which is 1.4 milliamps. So some very large currents compared to 20.52 microamps, so neglecting that seems also reasonable. For the base current here, we solved for this and it was 64.78 microamps, and the current that's flowing in here was equal to 1.026 milliamps, and that's about 15 times bigger than what we solved for here. Lastly, for transistor 13, we found the current here to be 61.6 microamps with a beta F of 50, and the current for I sub C11 was 1.026 milliamps. And that's about 16 times bigger than the current that's going in here. So those are reasonable assumptions. We've shown that the base current is positive, so that's one check. The second check we need to do is that the collector emitter voltage is big enough. In other words, bigger than a couple hundred millivolts. Find the collector emitter voltage of transistor 8. The work is on the next page. This node voltage is 6, and this node voltage here, I could go back to ground this way. 6 volts minus the quantity minus 0.7 plus 4.519 is 2.181 volts. So that is definitely in the active region. Transistor 10, we're going to solve for the collector emitter voltage, but we know the two voltages across it. It's 0.7 plus 0.7. Across here is 1.4 volts. Transistor 11, we could take the difference of two node voltages again. This node voltage here is minus 5.13 plus 6. This voltage here, which is 0.7 minus 6, and that quantity is subtracted from this quantity here. That turns out to be equal to 6.17 volts. And for transistor 12, we've got this node voltage here, which is 6, and then the output voltage we found was 170 millivolts. The difference of those two is 5.83 volts. In other words, about half the power supply is here and half the power supply is here, if this was 0 volts. Then lastly, for transistor 13, this node voltage is 0.17 volts, and then this node voltage is minus 6, so the difference of those is 6.17. So all of the collector emitter voltages are much bigger than a few hundred millivolts. So we are in the active region. So let's go back to the next page, where I did those calculations on the schematic, and here's the actual work. So now we can calculate the AC model. Again, we'll need a value of beta F to do this. Let's use 50. This is a suggested value in that application note by Motorola. RPi 8 is 8F E sub T over I sub B Q8. That was 28 microamps, so I get 929 ohms. RPi 10, the current was 31.18 microamps, that's 834. For 11, it was 20.52 microamps, 1.27 K. For transistor 12, it was 64.78, that's 401 ohms. For 13, it was 61.6 microamps, that's 422 ohms, and the betas will all be the same as the DC betas of 50. Now for transistors 3 and 4, which were diode connected, we have to find the value of RPi. But because of this short circuit, we have RPi, but then there's a current source in parallel with it. So what's the effect of that? For a diode connected transistor, where we're in the active region, and I'll call this the base and the collector current of transistor D, we could put in the AC model, which is an R pi between the base and the emitter, and then a current source between the collector and emitter of beta FIB. But now we're going to short the base and the collector. Let's apply a test voltage, measure a test current. What we're saying is that that has some equivalent resistance we're going to call R sub pi of D. Current I of T is equal to I sub B plus beta F I sub B. In other words, beta F plus 1 times IB. But the current I sub B is V test divided by R pi. I can substitute that back over here. I test is equal to beta F plus 1 times V test over R pi. And now we could solve for V test divided by I test. Bring the I test here, bring the R pi on the other side, and divide by beta F plus 1. The effect of this current source is to take the value of R pi and divide it by beta F plus 1. In other words, to make it small. R pi is equal to 8F V sub T over I sub B of our diode connected transistor. And we can write I sub B as I sub C divided by beta F. Bring that beta F up on top. 8F V sub T over I sub C of our diode connected transistor times beta F. Let's put this now into this expression over here by dividing by beta F plus 1. 8F V sub T over I sub C of D, beta F, and then divided by beta F plus 1. If beta F is large, it is approximately equal to 1. So I wind up getting 8F V sub T over I sub CD. You can calculate this resistance by using the collector current. Let's do that on the next page. For transistor D3, 8F V sub T over I sub C D3 was the same as the current in I sub Y, which is 1.559 milliamps. With an 8F of 1 and a 26 millivolt V sub T, we get about 17 ohms. For diode 4, which is a diode connected transistor, the current was 1.026 milliamps in the collector of transistor 11, which was also the collector current in D4, and that turned out to be 25 ohms. We got the parameters for the AC model. We'll look at in the next video is now doing the AC analysis and also a DC analysis alongside as we're beginning to calculate our way through the op amp. And this is partial analysis of a Motorola MC1530 op amp.